In this video, we finally take our first steps toward doing some real calculus. We're going to look at the limits of real valued functions. Our first step is developing our intuitive understanding of what limits are. We're going to use that to finally formally define limits, and then we're going to compute an example. So we're going to approach the limits of functions in very much the same way we approach the convergence of sequences. We're going to ask ourselves the question, what does it mean for the limit of f of x as x approaches c to equal L? Well, what that meant back when we were in calculus was that as x gets close to c, then f of x gets close to L. Sounds very similar to what we did when we were looking at the limits of sequences. X gets close to c means that the absolute value of x minus c gets small. And f of x gets close to L means the absolute value of f of x minus L also gets small. So that means we've got to set different standards for what it means to be small, right? Small is going to be different for the outputs than it is for the inputs. So if absolute value of x minus c is smaller than some particular number, we'll call it delta, then the absolute value of f of x minus L will be smaller than some given number. We'll call that epsilon. So every time we get an epsilon greater than 0, we can make absolute value of f of x minus L less than epsilon simply by demanding that absolute value of x minus c is less than our standard for being small, that delta. We got to keep in mind that we never want x to be equal to c, because we're letting x get close to c but never equal. That means our absolute value of x minus c has to be greater than 0, cannot be equal to 0. And so just like we did with sequences, we think of epsilon as Peeves' standards for being close to L, and then once Peeves gives us that, we get to give Peeves our standard of what it means for being close to c. And then all we say is, hey, as long as you meet our standard of being close to c, we will always be within your standard of being close to L. So here is our formal definition. So let I be an open interval on the real numbers. Let f from I to the real numbers be a function. And let c be in the domain. We say that the limit as x approaches c of f of x is equal to L if for every epsilon greater than 0, there exists delta greater than 0, such that whenever absolute value of x minus c is greater than 0, so x is never equal to c, and less than delta, we have absolute value of f of x minus L less than epsilon. So it looks very much like the definition of a sequence, except we don't have this notion of n being bigger than big N. We have this notion of absolute value of x minus c being less than delta. So as with sequences, here are some important points to keep in mind. The definition gives us absolutely no guidance on how to find the limit, only how to check if a given L works as the limit. That means we have to guess the limit and then verify it using the definition. Once we have found our limit L, or what we believe to be our limit, our top priority is to find out what is necessary for absolute value of f of x minus L to be less than epsilon. Again, our goal is to meet Peeves' standards. From that, we'll figure out what delta is. And it is true that we have different values of delta for different values of epsilon. We'd expect that. If epsilon is really big, we'd expect our delta doesn't have to be very small. But if our epsilon is tiny, we expect our delta to have to be very small as well. But we cannot have different values of delta for different values of x. Peeves gives us epsilon. We can give a delta back based upon that epsilon, but nothing else. And then once we have our delta figured out, we've figured out what our proof is so that it is in a nice linear logical form. So let's look at the limit as x approaches 1 of 2x plus 3. Using our intuition, it's not very hard to guess that the limit is 5, or if it isn't, we'll discover that it's something else, but we're guessing the limit is 5. So our proof strategy, or at least our strategy for getting ourselves towards being able to write a proof, let epsilon greater than 0, we want to see what is absolutely necessary for absolute value of 2x plus 3 minus 5 to be less than epsilon. So we could actually simplify that 2x plus 3 minus 5 a little bit. 3 minus 5 is negative 2. So we get absolute value of 2x minus 2 is less than epsilon. And very conveniently, we can factor out a 2 from that sum. We get 2 times the absolute value of x minus 1 less than epsilon. And that is actually very encouraging because we have absolute value of x minus 1 in there. That's very much related to our delta. So yay for us. So if we solve for absolute value of x minus 1, we get absolute value of x minus 1 is less than epsilon over 2, which suggests that our delta should be epsilon over 2. You can see that we get a different delta for different epsilons. And just whatever our epsilon that Peeves gives us, we take half that number to be our delta. All right, so that sets us up for our proof. Our theorem is that the limit as x approaches 1 of 2x plus 3 is equal to 5. And here's our proof. We start off, as always, by letting epsilon be a number greater than 0. And our goal is to find a delta greater than 0, such that if absolute value of x minus 1 is greater than 0 but less than delta, then absolute value of f of x minus 5 is going to be less than epsilon. And from our scratch work in the previous slide, we know that epsilon over 2 is going to be greater than 0. Epsilon is, so dividing it by 2 is still greater than 0. And we're going to let our delta be epsilon over 2. So we then assume that absolute value of x minus 1 is less than delta, and then show that absolute value of f of x minus 5 is less than epsilon. So delta is epsilon over 2, so we have absolute value of x minus 1 is less than epsilon over 2. And now we do the same algebra we did on the previous slide, except in reverse. We multiply both sides by 2. We multiply the 2 within that difference to get 2x minus 2 inside. Then we rewrite 2 as 3 minus 5 to get absolute value of 2x plus 3 minus 5 less than epsilon. We note that 2x plus 3 is equal to f of x. That's our function. And that means our proof is complete. All right, so now having seen that, I think you're ready to work on the activities for the introduction to limits. Just go ahead and click on the link below this video.